So it's a pleasure to have Shotaro Makusumi speaking on the curved Hecke categories.
Thank you for the introduction and the invitation. I'll be speaking about something that I've spoken about before, so I apologize if you've heard this talk before. I'm also a little bit sick, so I will be slower than usual, which is maybe good. So I'm going to be talking about some joint work in preparation with Matt Hogenkamp. We have a series of papers. We have a bunch written, but fortunately it's taking a little bit longer than I thought. Here's the main statement that I want to explain today. So let's take, for example, complex connected reductive group G, and let's also take its Langlands dual G check. Then associated to each one, you can define for us a monoidal triangulated category called a Hecke category. And my main statement is a kind of Langlands reconstruction for the Hecke category. More precisely, inside the Hecke category, I can take a specific object, some sort of causal complex, and then look at derive bimodules over this complex in the Hecke category. And that's equivalent as a triangulated monoidal category to the Langlands dual Hecke category. This is an interpretation, reinterpretation, and an extension of monoidal causal duality for the Hecke category that I studied previously with Achar, Risch, and Williamson. And I'll be referring to that paper several times. So I'll just say AMRW for those papers. But the new ingredients that go into my work with Matt Hogenkamp are something called the curved causal duality, and also box tensor product of type dA, A infinity bimodules. So a lot of interesting homological algebra. And I hope to give a sense of why curvature naturally shows up in when you're looking at a certain kind of homological algebra. Let's take a Coxeter system W with simple reflections S, and to it you can associate the Hecke algebra. I don't want to dwell on this for the moment, but here's my normalization. This has a standard basis. Let me call them delta W, and a Kajian-Lustig basis. I'll call them BW. So I want to start by explaining what I mean by the Hecke category, what version of the Hecke category I'm talking about. So this is a categorification of the Hecke algebra. So here's the standard kind of geometry here. Let's take G, connected reductive group complex, or even Kac-Moody group. And B is a Borel, and T is a maximal torus. And let's take a field of coefficients K. W is a Weyl group. Then G mod B is the flag variety. And on it, you still have the action of the Borel on the left. And so you can consider either the category of B equivariant sheaves on G mod B, or B constructible sheaves on G mod B. This first category here is monoidal for what's called a convolution product, whereas this one is not. It's only a triangular category, but it's a module category over this category. So I want to use this kind of stacky notation. Will come in handy later on. So this notation just means I'm looking at B equivariant derived category of sheaves on G mod B. And here U is the unipotent radical, and U equivariant on G mod B is actually equivalent to B constructible on G mod B. So the procedure that goes from B equivariant to U equivariant or B constructible is just to forget the B equivariance. So there's a functor this way. And also, as I said, this category acts on this one by convolution on the right. So we already saw parity complexes come up in this conference. This is a certain additive category inside this category. And what's important is that this gives you an additive categorification of the Hecke algebra. So in characteristic 0, these parity complexes agree with semi-simple complexes, and the decomposable objects are just the intersection cohomology sheaves. So their classes give you the causalistic basis in the Hecke algebra. But when you take K to have a positive characteristic, now you get some new basis of the Hecke algebra. And this is the p-causalistic or p-canonical basis that Tolga talked about in his talk. And maybe I want to emphasize that thanks to the work of Elias and Williamson, this category parity is, well, I mean, it has a geometric definition, but it can be understood in a completely combinatorial way. I also want to look at the B constructible version of that. And so I have the, just by restricting the diagram from before, now I get this diagram. Now I want to pass to complexes. So this is a definition of what Achar and Risch called mixed modular derived category. This is also the category that came up in Laura's talk on Monday. The same kind of mixed category. They define to try to imitate the behavior of mixed L-adic sheaves, where you have an extra grading shift in addition to cohomological shift coming from Tate twist. They define simply the mixed category as complexes of parity complexes. So in this category, already parity complexes are objects in the derived category, and so they have a cohomological shift. But also you've taken complexes of those, and so you have another new cohomological shift. And some combination of this plays has the features that deserve to make it called Tate twist. And this turns out to be a nice category where you can develop a lot of the kind of homological algebra that you have in you have a perverse heart, highest weight category, and so on. So for instance, there's a notion of standard sheaves, co-standard sheaves, delta W, nabla W that categorify the standard basis elements of the Hecke algebra. For instance, for a simple reflection S, the standards and co-standards are, if you're familiar with these things, they are what's called the Rukier complexes associated to these simple reflections. These ES and EID are the indecomposable parity complexes indexed by S in the identity, but in this case, they're the same as the intersection cohomology sheaves. So this is a constant sheaf on the corresponding P1 shifted appropriately. And this E identity is the monoidal identity of, so this is the skyscraper sheaf at the point stratum on the flag variety. Okay, so now I've just taken complexes and gotten this diagram. So I wanted to tell you about the causal duality. And at the Hecke algebra level, this is a ring involution. That's very easy to define by generators and relations. So if you look back for a second to the way that I defined the Hecke algebra, I normalized things so that the quadratic relation had this symmetric looking form. So that means that if I fix the delta S's, the generators, but send V to minus V inverse, then that defines actually a ring map, and in fact, a ring involution of the Hecke algebra. And this ring involution fixes the standard basis, but not the causalistic basis. So this is not the causalistic involution, for example. Okay. So a natural question is it possible to lift this to the categorical level? Can you, in other words, find some monoidal autoequivalence of the Hecke category that categorifies this iota, this ring involution? And well, at the level of the additive category of parity complexes, this is not possible because you have a minus sign here, but the standard way to get around that is to pass through complexes. So you could ask now, is there some monoidal triangulated autoequivalence of this monoidal triangulated Hecke category, D mix BGB? And if you look at the behavior of such an equivalence with two shifts in this mixed category, you can work out from this equation here, because V corresponds to one of the shifts, and -1 is a cohomological shift. You can work out that it should have this kind of behavior with the two shifts. And this is reminiscent of something in homological algebra called Koso duality. So we continue to call the resulting autoequivalence of the Hecke category or something related Koso duality also. So actually, you can do some computations already for SL2 and see that there can be no such autoequivalence. But instead, the situation is, I think, even more interesting. The right answer really involves the Langlands dual group. So let's take G check, B check, D check, T check. And this is one of the main results from this paper, AMRW. And we also replace, instead of the monoidal category BGB, we pass to the B constructible version. And on the right here, I've passed from B check equivariant to U check equivariant. But with that change, we show that there is indeed such such a triangulate equivalence that categorifies this involution iota. And I think that this is really a pretty fundamental phenomenon in Lie theory. And for example, if you take G to be finite type and K to be the complex numbers, then, well, after composing this with Ringel duality, this recovers the celebrated causal self-duality of BGG category O due to Valence and Ginsburg's orgal. And if you take G to be the loop group of some other reductive group and take positive characteristic coefficients, then this is related now to modular representation theory of reductive groups. And so this duality played a role in the proof of Riesch-Williamson conjecture on tilting characters using p-Kazan-stick polynomials. But I actually wanted to explain the monoidal version of this. So here's how you might motivate such a thing. So on the top here is the same diagram from before. Here's the, well, this is the additive version of the Hecke category, acting on the right by convolution on the B constructible version. And kappa is the equivalence from the previous page. But if you believe in this theorem, in this equivalence, then on this category, D mix UGB, there should also be some category acting on the left. Well, it's this category right here. So you can wonder if there's some category here, some monoidal category here, that's still defined in terms of G, not a Langlands dual, but is naturally equivalent to the Hecke category for the Langlands dual, and such that it acts on now the left of this category, D mix UGB. And you can do the same thing for the other side. These two vertical equivalences are what I'm calling monoidal causal duality, or well, additive monoidal causal duality. And this equivalence, if you care about symplectic duality, this categorifies the bijection of twisting and shuffling functors. So in symplectic duality, of which the causal self-duality of this category is an example, you have shuffling functors and twisting functors which are exchanged. And actually in this specific case, these functors actually come as the action of particular objects in these monoidal categories. And in this work, AMRW, we invented some category that filled those question marks to complete this diagram. So I should say, in characteristic 0, all of this was done by Bezer, Kotnikov, and Yun. And somehow, what we did is to try to give some algebraic analog of their constructions, which still makes sense in positive characteristic. So let me just give a flavor of this algebraic analog. Here are some algebras. The R is a symmetric algebra. Let's just take bases and say it's a polynomial ring in X1 through XR. And lambda is a exterior algebra in corresponding odd variables theta 1 and theta r. Then I can define the causal resolution of the trivial R module by defining this differential. And I also need polynomial ring in kind of dual variables y1 through yr. Let's call that R check. then here was the definition of free monotomic complex, an object of this question mark category that we invented in AMRW. Well, free monotomic complex is not quite a complex. It's almost a complex of parity complexes, but the differential is allowed to have some components which involve some odd variables on the left and also some dual polynomial variables, theta's on the left and y's on the right. And all of this data is required to satisfy not delta is the differential, delta squared is equal to 0, but some sort of curvature condition. And this term on the right is some central degree 2 element. And so this is a kind of Cartan-Maurer equation with curvature. So this is saying that a free monotomic complex is some sort of curved complex. And I think that we didn't really understand this definition when we wrote the paper and still for a while. And what I want to explain today is to try to give a, well, at least a conceptually better understanding of what this category is, and to yeah. Sorry, let me skip this. I know we're not taking breaks, but any questions so far? So I see a question in the chat. How do the Bezer-Kopnikov-Yun duality and the duality on the last page? Sorry, this was a while, but the in Bezer-Kopnikov-Yun, the coefficients were characteristic 0, and in fact, the categories involved don't even make sense in well, in positive characteristic. So yeah, already the definition of the mixed category is something that Achar and Risch had to come up with. Okay, so let me take the example of GL2. So in this case, R is a polynomial ring in 2 variables, x1 and x2. And the causal complex K is a 3-term complex like this. So this resolves the trivial module K, where x1 and x2 act as by 0 by free R modules. So you have these odd variables, theta 1 and theta 2 showing up. And K is not just a resolution, it has the structure of a DGA. Now, you can view K as an object in this triangulated Hecke category in the following way. Let's just take each copy of this R and note that R is the monoidal identity in R modules, and replace it with the monoidal identity in D mix BGB. Okay, now it's the skyscraper sheaf. So what I'm saying is actually this monoidal DG category of R modules sits inside the triangulated Hecke category. And so I can naturally view this causal complex as an algebra object inside the latter. Now, there was a definition in AMRW called left monogenomic complexes. And it had this funny notation where instead of writing UGB, remember D mix UGB would just be a complex of B constructible parity complexes on the flag variety. But now I put some fat backslash. And it turns out that one can reinterpret that definition as an extended twisted module over this causal complex. So what I mean by that is, let's take some object in the Hecke category. And then if I convolve it with this special causal complex, then this naturally becomes a left module over K. And then I can take some further twist of it. And for this whole thing to again be a complex, this additional differential delta has to satisfy this Cartan-Maurer equation. So this is a really nice kind of homological alternative to considering B constructible parity complexes. So as I said, usually the passage from BGB to UGB is done by taking B equivariant sheaves and then forgetting the B equivariants to pass to just B constructible sheaves. But you realize that the difference between B and U is you're killing the action of the torus essentially. And
Mackie, are you muted?
I don't, yeah, we're losing you, or I wasn't sure whether it was me, but.
Looks like we've lost him.
Can you hear us? Let me write to him. Are you hearing us? Okay.
Mackie looks like he's talking.
Oh, I just tried to unmute him.
Can you hear me now?
Oh, yes, yeah. Good.
Hi, can you hear me now?
Yes.
Maybe a little bit louder would be better, but we can hear you.
Okay, let me see. I just switched device, I think. I don't know what happened. How about now?
That's good. Thank you.
Okay, great. I think that my my sharing device Must have lost the internet or something because the screen is not updating. Let me see if this works. I just tried to, can you hear me?
We can hear you, yes.
Okay. Yeah. I'm sharing again from the device, but I'm not getting anything. Oh, start share. Oh, here we go. Okay. I think I have to override. Sorry about that. How far were you able to hear me?
You didn't write, the dream line had not appeared yet, and you were just commenting about the fact that this construction was replacing the
yes.
UGB. You were just
right. Okay. So just to emphasize the key thing here was that this new category is it's equivalent as a triangular category to this old version, but not as a DG category. I mean, in the same way that the causal complex is quasi-isomorphic to the base field, but not isomorphic. So the dream then is to see if you can define this category D mix UGU, which would be the thing that acts on this is the monoidal category that should be, that was in question mark. If we could define it also with the same kind of procedure. So what turns out to be right is you can take some notion of derived category of K bimodules. And you can already see that there are going to be some difficulties with this definition. The derived category, again, is just an ordinary category, not a DG category. And you can give it several DG models. Now, the easiest one is the way you usually define derived categories is to resolve each object. But for instance, in that case, the monoidal identity of K bimodules is K itself. But this is not free as a K bimodule. So in a DG model, if you wanted to try to get a monoidal DG category, you see that you have an issue because now you have to resolve this K as a K bimodule, but then you lose unitality at the DG level. So in this DG model, you do have bifunctoriality of your monoidal product at the DG level, but it's only unital up to homotopy. Now there's another interesting model for derived bimodules called type D A infinity bimodules and box tensor product. And in this case, the monoidal identity really is just K. And so this product will be DG unital, but it will only be bifunctorial. The monoidal product will only be homotopy bifunctorial. So you can see that if you're familiar with the original paper of Bezirkovnikov and Yun, where they construct their geometric version of this category, there's a lot of geometric technicalities involved, and as a philosophy, we try to replace it with some correspondingly complicated homological algebra. But in some instances, you can really see how the geometric complication matches up with the homological complication. Let me skip this. So I want to tell you about a phenomenon in homological algebra called curved causal duality. And this kind of explains why the AMRW definition is the way it is. So classically, causal duality relates two graded algebras. The most classical example is between a symmetric algebra and an exterior algebra. There's a more modern formulation of causal duality that's due to Keller and his student Lefebvre-Segawa. And their idea is to replace the causal dual algebra by a coalgebra. So their starting input is actually a triple consisting of an algebra, or maybe DG algebra, a coalgebra, and some structure relating them called a twisting cochain, which is required to satisfy some sort of Cartan-Mauer condition. And from this data, what they can show is, so from this data, there's always a way of taking a DGA module and a DGC co-module and tensoring them together using the twisting cochain. It's called a twisted tensor product. And in particular, you can take any C co-module and tensor with A. That gives you a module, and vice versa. And this always gives you a DG adjunction between these two DG categories. And Keller and Lefebvre-Segawa say that tau, or this triple A, C, and tau, is acyclic if this adjunction actually induces an equivalence of suitably defined derived categories.
I mean, can I just a question? The page before in causal duality, one of the V should be dualized, isn't it?
Sorry. Yes, one of the V should be dualized. You're right. Yes, this.
And exterior algebra V, one is dualized, and the idea with the Keller, if you do algebra and coalgebra, you don't have to dualize anymore.
Yes,
correct?
That's right. Yeah, and also many finiteness conditions that you have in causal duality usually disappear if you take co-modules.
Thank you.
Yeah. So here's another way of stating what Keller and Lefebvre-Segawa do. So, well, it's the usual story in causal duality. Starting with any algebra equipped with an augmentation, you can consider its bar construction. So this is the kind of structure that, for example, can be used to give a functorial resolution of any module. And this bar construction is it has a natural coalgebra structure, and it's always causal dual in this new sense of Keller and Lefebvre-Segawa to the original algebra A. So this A and the bar construction are related by some universal twisting cochain, and this is acyclic. But the bar construction is huge. And so if you want to compute things, for example, then it'd be much better if you have some smaller, so quasi-isomorphic is not quite the right word, but weak equivalent. You want to try to replace the bar complex with some smaller coalgebra C. And this is basically the idea of causal duality. So an algebra A and a coalgebra C are causal dual if C is is a coalgebra that is weakly equivalent to the bar construction of A. And I want to apply this to the causal complex. So this is the same causal complex from before. But now there's an issue. Remember in Keller and Lefebvre-Kasegawa's story, there was a augmentation required. But I want to regard the causal complex as an algebra over this polynomial ring R. And then in that case, the augmentation should be a map from the causal complex to this symmetric algebra. So it just kills the exterior part. But that map is doesn't commute with the differentials. So it's not a DG algebra map. And so it's not an augmentation. You can't carry out the same construction. But in that case, Pozitelski has a paper called Two Kinds of Derived Categories, something. And I mean, he has many powerful ideas in this work. But one of them is that in causal duality, if the algebra side lacks an augmentation, you can compensate for that by allowing a curvature on the coalgebra side. In fact, the bar construction itself already has some natural curvature associated to it. And over this curved coalgebra, one should consider curved DG coalgebras and their categories. And that's the kind of, and you should consider their derived categories, suitably defined derived categories, when formulating causal duality in this setting. And so in our application to the Hecke category, we have to take this idea seriously. It actually turns out that the curved complexes that were showing up in the definition in AMRW actually correspond naturally to a coalgebra, a curved coalgebra. And it turns out this is a divided powers coalgebra is a causal dual to the causal complex. And this really explains a lot of the homological algebra that was developed in a kind of ad hoc basis in those papers. Sorry, let me skip this. So with this motivation from curved causal duality, here's Matt Hogenkamp and I, our proposal for a new definition of D mix UGU. So this is essentially a reinterpretation of the definition that was given in AMRW, and I tried to give you a taste of earlier. I said that on the left in that definition, there were some odd variables. And on the right, there were some dual polynomial variables together with a curvature. But actually, you can package all of that neatly by saying we're really looking at an algebra object K, a causal complex, a curved coalgebra object gamma, some it's a curved divided powers coalgebra. And what we're looking at is really curved DG modules, co-modules over such things in the Hecke category. Now, this curved coalgebra is causal dual to K. And so this is just a way of giving a smaller model for the bar complex of K. So now if you replace this gamma by the much bigger bar complex of K, then here's a new definition of a category. We like this, an even fatter slash on the right. And these are what people call type DA structures, or type DA A-infinity bimodules over the causal complex K. And this is known to be a kind of a model of derived bimodules that's smaller than the usual one involving A-infinity product. Now, the advantage of this new definition is that it's much easier to prove certain things. So, for instance, it was very difficult from this old definition to show that this category was even monoidal. But that's actually some much more standard homological algebra, essentially because the bar complex is such a nicer object to work with. And also, this category is more obviously triangulated. It's a triangulated monoidal category.
So Kenneth, do you have the monoidality already at the A-infinity level, or you didn't check everything? You only checked that after localization. It's
I mean, I don't know if this is it true that type DA bimodules form some, so I actually don't know what monoidal A-infinity category is precisely, but I mean, I'm not using any crazy new kind of homological algebra here.
Okay, but you have to check, I mean, for example, the associativity of the tensor product, this type of issue. I mean, it's an associativity. I mean, the objects are, it's not a category, it's an A-infinity category you start with, correct?
So I'm starting with, okay, A-infinity modules form a DG category. And CDG modules also form a DG category.
Yes.
So so really this is DG.
Okay, so you're at the DG level from the start.
Yeah.
Okay. That answers my question. Yeah. Thanks.
Okay. Yeah. Yeah. I don't know if there is something more general I should be looking at. So I know at least there are these QDG modules which we use in this paper also, which form a CDG category. But I don't know something analogous for A-infinity. I'd be interested to chat later. Okay, so here's the updated picture now. I'm sorry, there are so many categories, but this is kind of the nature of the work. So here's the picture from before. Here was the Hecke category, the monoidal version, and it acts on the left of this constructible version. Sorry, on the right of this constructible version. And then I upgraded this to a fatter backslash here by using the causal complex on the left instead of the trivial module. But now what we've done is we now have this category of some notion of A infinity bimodules over K. And so this is a monoidal triangular category which naturally acts on the left of this category. So yeah, it's if you just focus on this category, and then this category, then here's the category in the middle being acted on the right by this Hecke category and on the left by this funny new category. Okay. And the statement is then that this new funny category that we've defined really is equivalent as a monoidal triangulated category to the Langland's dual Hecke category. So this is the Langland's reconstruction of the Hecke category that I had promised at the beginning of the talk. Okay, let me actually stop there, I think, and open up the questions.
Okay, thank you very much. Are there questions or comments? So I have a question. So do you need to deal with new types of formality-like issues to do what you're doing, or?
No.
Okay.
So I never consider, for example, trying to pass from any mixed to unmixed version, say. Yeah.
And so what you've done there would presumably work in a more general, I don't know, like parabolic setting or something like that. I mean, the construction of this or in a non. I mean, I don't know if you're doing that directly for Sauger bimodules. You could do it in a Kac-Moody case, or
yes, exactly.
all,
so
okay.
Yeah, in fact, you can just replace parity with the Elias Williamson diagrammatic category, and you can repeat this whole construction. And so it should lead to a causal duality statement that works for an arbitrary Coxeter system. And even more, I actually have some version that tries to upgrade this to a triply graded equivalence. Yeah, let me just say very briefly. So right now everything is all these categories are doubly graded, but if you so this is basically I'm adding the Hochschild grading motivated by Kovanov's construction of Humphrey homology. So if you replace parity with Zorgel bimodules, so for now this only works for finite type, but Matt and I conjecture that if you then replace Zorgel bimodules with if you view it as sitting inside the derived category of R bimodules, so you pick up another cohomological shift from there. Then also together with that enhancement, you can still do this construction, and you would still have this kind of equivalence. So yeah, I just want to, I guess the most of the paper is developing a lot of homological machinery, which will apply pretty generally.
Thank you. Other people, other comments, questions? No. Okay, so let's thank Shotaro again.